Hello DE students. Today we're going to be taking a look at AOI design. This is going to be using truth tables and converting those truth tables into logic expressions. So we're going to be covering how to properly construct a truth table. We've looked at truth tables a little bit when we talked about binary, but we didn't go into a ton of details. So we're going to be taking a closer look at those today. We're then going to use those truth tables to write a sum of products or SOP logic expression using that truth table. And then we're also going to do the reverse of that. We're going to take a truth table and create it based upon a given logic expression. And then we're also going to create a truth table from a set of design specifications, such as a word problem. So really this is taking this binary truth table and figuring out how we actually need to work to create circuits based upon that information. So when we look at constructing a truth table shows how logic design's outputs respond to all of the possible combinations of inputs. So a logic design with n number of inputs will have 2 to the n input combinations. So that's just how we can figure out how many we're supposed to have. The inputs are listed in binary order, so basically counting order in the columns to the left, and then the outputs are listed in the columns to the right. Now, some logic circuits can have more than one output, so those truth tables look a little bit different, but in general, the formatting is that our inputs are listed in binary order on the left, and then our outputs from those inputs are on the right. So if you look at this, this is a format for a truth table. We have the inputs X, Y, and Z. They're in binary order starting 0, 0, 0, 0, 0, 1, and in counting order from there. So for input combinations, we have 3 inputs and a total of 8 combinations, and that's determined because 8 equals 2 to the third. Then we have our outputs. Output is labeled as F1 in this chart, and then this is the combination for all of our outputs based upon this. So again, you can note the binary output, we have the counting order, and then our outputs on the right. So these are some example truth tables. So here we have a truth table with 2 inputs. We have input A and B, and F2 is our output. You can see again we're in binary counting order starting at 0 and counting through. Then we have our 3 input combination table, and again 2 to the third means that we have a total of 8 combinations, and then with a total of 4 inputs, 2 to the 4 gives us a total of 16 combinations. So again, this is a binary counting order. That's how we can just calculate through and figure out what our inputs are and our outputs are going to be for our truth tables. Okay, now taking that truth table and turning it into a logic expression, you can write the minturn, okay, adjacent to every row in the truth table that contains a 1 in the output column. So basically anywhere that we have a 1, that means we're actually getting an output. When we say a minturn, we are talking about these expressions right here. So this minturn is saying x naught, y naught, and z give us an output. Down here it's saying x naught, y, and z give us an output. Here, x, y naught, z naught gives us an output. And lastly, x, y, and z naught, that's that line above there, give us a 1. After we've written all these minturns, we can then turn this into a logic expression. So we take all of these letters and we put them into a sequence like this. So F5, which is our output, is equivalent to x naught, y naught, z plus, or and, x naught, y, z, and x, y naught, z naught, and x, y, z naught. So basically these are the possible combinations we can have to get an output for this F5. So let's walk through this example. So you're going to write the SOP logic expression for the output F6 in the truth table below. So the first thing you need to do is identify the different outputs that have a 1 listed in them. So we have 1, 2, 3, 4, and 5. So we have 5 different minturns that we're going to identify. Okay, so this first one is A naught, B naught, C naught, D. Then we have A naught, B naught, C, D. A, B naught, C, D. A, B, C naught, D. And then A, B, C, D. All of those then get transferred into our SOP function right over here. So we write the minturns, turn them into our function. Okay, now for each term in the logic expression, you need that place a 1 in the output column for the input condition that matches the term. So some terms may match more than one input condition. So what we're doing is that we are looking at, so we're going to create the truth table for the following logic expression. So basically we're taking this when it's x naught, y naught, z naught, so 0, 0, 0, gives us a 1. Okay, x and z gives us, is actually condensed from further down, and then x naught, y, z, oops, is filled in this area. So you can see x and z, both being a yes, is filled in anywhere that we have a 1. So the y, as soon as that fades away, sorry guys, the 1 for the y is irrelevant. So whether the y is a 0 or a 1, it doesn't matter because we are looking for instances where we have x and z. So let's take a look at the second example. So we need to create a truth table for the following SOP logic expression. So we have A, B naught, C, D, A naught, B naught, A, B naught, C naught, D naught, B, C naught, and D. So we need to lay out our inputs for our truth tables A, B, C, and D across the top, and then F8 would be our output. After you have that, you're then going to identify the different function areas and put a 1 for the output. Anywhere that we don't have an identified output then gets a 0. Okay, so now let's take a look at design specifications to a truth table. So this is where we're talking about word problems. So you have to identify the number of input variables. Okay, so after you've identified the number of input variables, you need to assign variable names and establish the assignment condition for each variable. So what does a 0 or a 1 mean for that input? And then from there you create the truth table. So the example we have is that a large fuel tank has sensors that monitor temperature and pressure. Both sensors output a logic low if they are within safety range. An alarm will sound if either sensor indicates an unsafe condition is present. Create a truth table for this logic design. So down here then we see P, which would be pressure sensor, 0 is safe, 1 is unsafe. T for temperature, 0 is safe, 1 is unsafe, and then the alarm, 0 is off, and 1, the alarm comes on. So we can establish our truth table by going, okay, if P is 0 and T is 0, the alarm does not come on. If P is a 0, T is a 1, the alarm needs to come on. If P is 1, T is 0, alarm comes on, and obviously if both inputs are indicating high, then they both come on. So that's how we take our information from a word problem, turn it into a formatted statement, and then create a truth table from that. Okay, so let's take a look at another example. Your teacher keeps her final exams in her office. For security reasons, she would like you to design an alarm system for her office. The office has a window and a door that are equipped with sensors that output a 1 when they are secured, closed. When the alarm system is turned on with a key, the siren should sound if the window or door is unsecured, opened. So looking at this, the key, okay, the 0 would be system off, 1 system on. The door sensor, 0 if open, 1 if closed. A window sensor, 0 if open, 1 if closed, and then the siren, 1 is on and 0 is off. So we then need to indicate the different inputs K, D, and W, with S being our siren as our output. We then need to go through the different situations and determine when we get outputs. So as you can see, we do not get an output until we get down to K being 1 and D and W being 0s, because if the key is not on, the system isn't on. So until we get a 1 in the K column, none of these are going to function. All right, that concludes the examples of the AOI Logic lesson. If you have any questions, please let me know, and then move on to your activity.